Okay, so let's go back. So did you manage to to complete the first script? So here is some solution. So I will show you one way to do it, of course. So for the first atom, the position, okay, it could be 0 here, actually, the first atom at the origin, and the second atom at one atomic parameter along the z-axis. So here is a way to rotate 45 degrees along the y-axis. So this is a method from the chain ASC chain object. And as the first atom of the chain is the emitter, you just have to put 0 here. Okay, very simple. And then for the calculation, so here you choose a spectroscopy. So this is PED, of course. The algorithm is expansion, for series expansion, and you set the atoms to the calculator. So the chain will be used for the calculation. And you will tweak the parameters, so the scattering order. So here, single scattering means scattering order is 1. And you choose the level of the Nickel, so the 3s level, for example. And here is the theta range. So this is a NumPy array, but it may be also a simple Python list. Okay? And this NumPy array, you can produce it using NumPy arrange, NumPy lint space, log space, whatever you want. So this is in degree, not in radian, in degree. And all data.view. Okay? So I will upload this script on the TMP file, on the TMP folder here. So here now on the TMP folder, in the copper directory, so you have the script, the full script, in the copper correction directory. So if you want to copy them, unless you did it properly. And here I will copy this one for the Nickel. So okay, let's do this like this. Okay, so this is the full script for just 2 atoms of Nickel. So if you run it, okay, you should have something like this. So if you view your cluster, you have only 2 atoms, okay. And of course, the absorber is this one, or emitter. And you have your forward peak. The forward focus is at 45 degrees. Okay, so everything is logical. So now your work is to modify your script to add 2 nested loops over the chain length. So you will grow the chain, add more atoms. So up to 5 atoms, and over scattering order from 1 to 5. 1 and 5, actually. So you will compute the multiple scattering polar spectra for scattering order 1 and 5 for 2, 3, and 5 atoms to see the defocusing effect, like in the paper. So here we go. 4.
5 or just 1 and 5?
For the scattering order, so it's up to you, but just stick to the paper, so 1 and 5, for example. At least so the thumb rule is that when you use the series expansion algorithm to make a calculation, you have to use a scattering order which is at least the number of atoms up in front of diameter along the path. So if you have, for example, a chain of 5 atoms, it means that you need at least scattering order 4 to have a reasonable description in multiple scattering. So you understand here very well that if you want to use a level that is not so much a core level, you will have a high kinetic energy, so a very deep mean free path of the photoelectron inside the substrate. So you will have to compute at lower plane to see the results. So the scattering order will be high, so the calculation will be long because of the scattering order and because of the size of the cluster. And it will be impossible to treat this with inversion because it is too huge. Okay, is that fine? Do you manage to do it? Yeah? Is someone completely lost? No? It's fine. So I propose a solution. So we will have something perhaps close to this. So can you read? Yeah, barely. So for chain length, so it will be my variable for the chain length in the list, so 2, 3, or 5 atoms. You can even try 4 atoms also. So the nested loop is for order in 1 and 5. And then you mostly copy-paste the preceding script. okay, to create your chain. So here is this kind of notation is very Pythonic. So I don't know if you are aware of this. So this is called list comprehension in Python. So you see that I'm creating an atom object here for index in the range chain length. So range chain length will produce a list that is composed of index from 0 to the maximum chain length, -1, okay? So range 2 will produce 0, 1. And here, it will produce each object in the list. So this is an atom of nickel positioned at 0, 0, I times A. So 0, A, 2A, 3A, etc. Okay? Then you copy-paste the rest of your script. This is exactly the same, but here you take care to put the variable order to make the calculation, and you use the same function, and it will compute this for all chain length and all orders. Okay? Appending the data on the all data object. So here is an optional part that you may not guess, of course. It is to use a useful title for your data set. So the all data variable is a data object. Inside the data object, you have data sets. Okay? So when I want to pick up the last data set that was created, appended to the file, to the object, I just need to write all data and in square brackets the -1. So this is the last data set that was uploaded to the data object. Okay? So this is the data set, and there is an attribute, the title, that I can change. And this title may be more representative. I give you the order number and the number of atom in the chain. Okay? So it starts to be more Pythonic.
How could we accumulate the data set into the data instead of overwriting?
This is not overwritten, actually, because you specified all data that was existing object. So the first time, if this object is none, it will create a new one. But the second time you put it in there, it is appended. Okay. So this is not overwritten. If you want to overwrite, you should specify overwrite is equal to true.
But then if I do only one view, it shows only one
calculation.
Only one calculation.
If you do only one calculation, you do not have to specify data.
No, what I mean is, so I made all the calculations and called view at the end only, and I still see only one.
Look in the dataset menu. You should have several datasets. Okay, for this, so I will. Okay, so and lastly, this each dataset is attached several views. Okay, you have a dataset with several columns, and you can plot these columns, and you can plot, for example, column 2 versus column 1, and column 3 versus column 4, for example. So there are two views, for example, for one dataset. So you can attach several views to a dataset. To get all the views, you just have to use the dataset.views. So it retrieves a list of all views. And if you want the last views, you just use the -1. This is a Python list, after all. And you get it. And you can change the title of the view. So this is more complex, but it is just for example that it is possible to tweak the view of the data inside your script. Otherwise, it is not mandatory. You are not required to do this. You can just run the calculation and treat your data as you like. But it is possible to make some treatment, some plotting option inside the object. This is just an example. So I will upload this file so that you can get it. Okay, so this is file number 01. And I can run it to show you. Okay, so this time there are at least 3 to 6 calculations, I guess, yeah. So here, I don't know if you can see everything, yeah. So here is the data set. So you have order 1, 2 atoms, order 5, 2 atoms, order 1, 3 atoms, etc., etc., etc. Okay? And so to sum up the results, you should obtain something like this. So for 2 atoms, here is the result. To order 1, you see a growing peak. Order 1, yes, you see a growing peak. Order 5, you see that the pink is damping. Okay, growing peak because of the scale. Actually, is it supposed to grow? Yes, it's supposed to grow. So, okay. So this is for the forward defocusing effect, and you see now how to use loops in your script to modify some parameters and to append data, to have several data sets on your calculation so that you can get the evolution of the PED against the phi angle, for example. You can treat several azimuth angle, chain length, energy, whatever you want. All right? Okay. So let's move on something again important. So this is so this is the scattering factor. So Didier told you about the scattering factor, and I show you a sketch of this this way of redistributing the photoelectron intensity after a scattering event. So there is so this is an important parameter, and it is always very nice to be able to compute it, to have an idea of the shape of the scattering factor as a function of the angular position, of course. So there is here, if you do the calculation, for example, for 2 nickel atoms, so when the photoelectron will be scattered by a second nickel atom, if the energy is very low, for example, 10 eV, you see the shape of the scattering factor. So there is 2 lobes, but one lobe is more pronounced in the backward direction. So you are more willing to get backward than to get forward. And if you increase the energy, you see the shape can be really, really tricky. So it is sensitive, of course, to the photoelectron energy and to also the electronic structure of the scatterer. Okay, so this is for example for the nickel. But as long as you go higher in energy, you will produce a really forward direction and somehow, in some extent, a backward. Some backward also, some backward scattering factor here. And if you move to very higher energy, for example, close to 1000 eV, you have only forward focusing effect. Okay. So, in a work back to the 1999, the group of Osterwalder, they did a very interesting work. So they were able to absorb oxygen onto a rhodium surface. Okay, and rhodium is a very huge atom, and it has even at high energy, it has a quite high backscattering factor. So it means that electrons that are emitted from oxygen, that are emitted towards the rhodium atom, they have a chance to be backscattered and to interact with directly emitted electrons from oxygen. So, and they will construct interferences. And this kind of interferences will be used to infer the position, the absorption site of the oxygen atom onto the rhodium surface. And they were also able to measure the height of the absorption oxygen, the absorbed oxygen, within a range of error that is really, really small. Okay? It's kind of atomic interferometer. Okay? So you will compute this and demonstrate that it is possible to make such interferences and to have such a precision to measure such distances. Okay? So I guess I uploaded everything sorry about that. I guess I uploaded everything in the TMP folder. Normally you should have the paper, which is based on this. So it's a APIL. So it's not very long. It's you can take time to read it just to have the gist, but really this is a brief summary of what they did. And then the first step is to be able to reproduce the figure that is in the paper. So you see that figure? So they sketched the emitter and the scatterer here. And this, so this is the atom, actually. This is the radius of the atom, okay? And here is the computed scattering factor for oxygen. And this is the computed scattering factor for the rhodium, okay? At the same kinetic energy. And we can clearly see that there is a strong backscattering factor for the rhodium compared to the one of oxygen. So my first question is, how large is this scattering factor of rhodium versus the one of oxygen? So for this, you will have to compute the scattering factor. Okay? So just build a system with 2 atoms, compute the scattering factor, and tell me. All right? Okay, so this is not too hard Python for those who are not used to Python. Yes, it's fine. It's okay. Okay, so let's help a little bit. Some starting point. So then usually after creating the cluster, what would be great? The 3-step, create your cluster, then create the calculator. So the calculator, no surprise, spectroscopy, set atoms, cluster absorber 0. And finally, compute. Okay. So in the paper, it is specified so the kinetic energy 723. So usually, yes, in the papers you have to be careful to try to pick up all information that is given. So as I said before, the detector geometry, if this is given. No, this is really often that this information is missing. Of course, the input energy light, and sometimes this is missing also, so you have to guess. Okay, so how large? What is the ratio between the backscattered, the backscattering factor of rhodium and backscattering factor of oxygen, roughly? Yeah. Actually, yeah. This is about 10, precisely. Very nice. So the unit of the scattering factor, actually, this is homogeneous to a distance. Okay. So this is in angstrom. Yeah. Right. So this is consistent with their publication. So, yeah. We start now to something more interesting. So we know that it is possible to be backscattered by the rhodium. And now we have to compute this cluster. So they used single scattering experiments. So we will do the same. I guess I use also single scattering. So this is possible because here we have a very, very small cluster. Okay, only 3 atoms of rhodium, 1 adsorbed atom of oxygen, and the emitter is the oxygen atom. So it means that if you take into account only single scattering, it will be normally enough. Okay, so try to build this rhodium surface. So the problem here is that this is not a bulk structure. This is a rhodium 111 surface. So you cannot use the bulk method from the ASE package. You have to look for a special function that can construct a such sort of a rhodium 111. So rhodium we are first to figure out, yeah, this is FCC, so it is total. So rhodium is FCC. So a FCC 111 surface. Then you have to use a function of ASE to absorb an oxygen on the FCC site. You can place it at a given distance from the given height. And of course, don't hesitate to use cluster.edit or view cluster to check that you are not messing all around. Okay, so I uploaded the first script in the TMP directory. So for this second calculation, it is better to use another file, okay? Or you can use the same file, but you have to move everything you did for the scattering factor to a function, so that not to call it during the second calculation. It's not really dramatic because it's a very short calculation, but it will avoid to compute this a second time. Okay? So let's have a look. So in the build module in ASE, you have this FCC111 function that is very handy to produce FCC111 surface, of course. And the add adsorbate function that is very handy to add an adsorbate on a substrate, of course. So how to create the cluster? So this time, so no need to use the hemispherical cluster function like for the copper example. You can just use, because this is only 3 atoms, so if you use the FCC111 function from ASE, you have to specify the size, the repetition. So the size of your surface. So 2 atoms along the first vector, x, 2 along y, and 1 along z. So 1 layer, 2 by 2, okay? So it will produce 4 atoms, actually. But this is only 3 atoms. So if you use cluster.edit or view cluster, you can see that you have to remove the last one. So as a cluster or atoms object from ASE is just a list, you can just pop this one, pop the last one. And you will have a cluster of 3 rhodium atoms. And then you use the add adsorbate function. So you must specify the host, so this is the cluster, which kind of atoms object you will put on this site. So it may be an atoms object, but if it may be also a string, so here an oxygen atom, the height of adsorption, and the position. So for a known surface, you just have to specify the name of the adsorption site. It is known. So for rhodium, I guess there is the FCC and the HCP site, I guess. So there are 2 sites, and they are known to the function. So if you specify FCC keyword, FCC value to the position keyword, it will put your oxygen atom on the right side. And this is normally given in the documentation of the function in ASE. And this time, the absorber, so is the oxygen atom, and it is the last atom added to your cluster. So it is the size of the cluster minus 1, because numbering starts at 0 here. Okay? This is quite straightforward. And then we move to the calculation part. So you have to construct a calculator. Calculator that may calculate this time a theta phi scan, okay? Like in the paper. In the paper, you see okay, so they are studying here the shape of the interference, what may be the origin of this. But here are the results. So the experimental results is over there, and here are the results of the computation. Okay, so the sketch here is just to help you to see where is the FCC site, but in reality they just use 3 atoms, 3 rhodium atoms and the oxygen atoms, and the oxygen atom. So such stereographic projection. So you have to find which function is used for this. This is because you are so quiet. All of you are tired. So what is the name of the function to compute a stereographic projection? You know?
Yes, beta pi.
Yeah? Okay. So did you manage to construct a calculator? Yeah. So easy. Create the calculator as usual. So you use the inversion algorithm. So contrary to what I said before, this is not expansion, this is inversion. So this is multiple scattering. In the publication, this is single scattering. And then you compute. So you choose the 1s level of oxygen, of course, the kinetic energy was given, so this is 723. And you can pop up the results, and you should have something like this, stereographic projection, so you can see. So this is actually the image of the rhodium atoms, okay? And then so I will upload this script for those who were not able to do it, but you have to modify the script. Like before, for the nickel chain, you will add a for loop to vary the absorption height of the oxygen. And you will see the difference in the diffraction pattern as long as you move the oxygen on top of the rhodium surface. So let me share this. Okay, so the script for just one height of the oxygen on top of the rhodium is a 01, the 01 script. So you just have to modify this one, add a small for loop to vary the absorption height, and being able to tell me what is the bond length difference between two intensity maxima. So when the center of each rhodium atom moves from maxima to another maxima, to another maximum to another maximum, or from a minimum to another minimum, how much should I move my oxygen atom? It will give you an idea of the accuracy that we may have to measure a bond length. Sorry?
Is this going to be from the graphical output, or do we need to do some post-processing on the data?
Normally, from the graphical output, you can have the value of the intensity when you move the mouse on the stereographic projection. So for the value of the intensity. But here, you will make a loop. So you will make many times this calculation, many times. At least, let's say 10 times this calculation with a different height of the oxygen. Okay, so you will have 10, for example, stereographic projection, and each time corresponding to a different height. Okay, so when you see that for one height of the oxygen there is a minimum of intensity, you will monitor the other height of the oxygen giving rise to another minimum of intensity. And the difference between those two heights, this is the number that I am looking for. Okay? How far should I move my oxygen atom between two maxima or two minima?
was running the calculation. It went through
Mm.
3 sites, 3 entries
Yeah,
in
that's-
the loop, and then it
Yeah.
crashed.
And you are
Like
connected to the Hawk session?
that.
Oh.
Yes, but it has something different matplot. Is it maybe
Yeah.
with graphical display? Because
Also, my God, if you have the problem, maybe everyone will have the problem.
there was on my computer there was before a problem with graphical display. Okay.
Did you manage to display also the scattering factor? It was possible for you to
Yes.
display them?
Yes.
Ah.
This also I will run it. Maybe this one it will.
Oh, okay, so maybe we will run into trouble for displaying the stereographic projection output.
But
Ah, no,
This one-
I see someone is managing this.
this
Ah,
one is
okay.
displayed. The next one is. But okay, if it's a.
Okay, so you did a loop and you,
Oh,
you,
the one
you,
is
you let the data view in the loop.
Yes.
So it will display each time it will pop up a window.
Yes.
Okay, so
It's
so
crashed at some time.
yeah, so you will remove data.view
Mhm.
from the loop because you are doing all the calculation. It is appended to the end of the data each time you make a calculation, and in the end, only one time you call data.view
Oh,
to
okay.
see all the
I got it,
data
I got
set. You understand?
Yes.
Okay.
Now I do. Thank you.
This first question about this. Sorry. I want to conduct this calculation,
Yeah.
but so I write
Okay. Yeah. And it crashed.
cross the error message is from
Okay, so this is not error message. This is just information.
Oh.
So here is the start of the error message. Okay, actually. So what is going on? So didn't manage to find an energy. So can you show me the script, please, again?
Oh.
3s theta ni. So to me it's correct. Perhaps it corresponds to this is the right distance. Yeah. This is 3.9 times 0.7, so it should be something like this. Yes, why not? So can you run it again?
Oh.
So Python. Python, yes, Python ni.py. Can you run it? Python? Yeah, sorry. Yeah, space ni.py. Okay. May I see? So. Sorry. Oh, yes, close terminal. Yeah. So, is it the tab? Completion works? No. MsSpec. MsSpec. Tab.
So it is.
Okay. So let me do this. So P WD. So Hogfancat MsSpec. Okay. So CD T M P LS MS. Okay. So CD MsSpec. Tutorial. Where's the star? Okay, yes, okay. So CP, VI, just to check, VI. So this is 0, 1, 1 dash ni underscore.
Shift on.
It is hidden. I'm sorry. Chain, okay. And the script is yeah. Okay, so yeah, I am a chain. So this is the second, no, the first one. This is actually, yeah. I'll try to use this one. So the chain is not rotated. Yeah, did you rotate the chain? Use expansion. Okay, so try to use this one. Okay, exactly this one,
okay.
Because perhaps the distance is too compact.
Yes.
Perhaps this is this. And rotate the chain, because I'm not sure that the chain was rotated for you.
Okay. Yes.
Not sure. So that you can see something, because otherwise you see here you are computing from 0 to 80.
Yes.
So if you do not rotate the chain, the result will be only at 0. So you won't be something. You won't see anything. You won't see all the things. Okay.
Yeah.
So try to this, and if it doesn't work, I will check back. Okay, so is someone succeeded? Does someone succeeded in a?
Question: do we need to reinitialize the calculator every time within the loop?
Do we need to?
Just trying to reuse the calculator object. This was not working.
Yeah. So yes, it's better to create another calculator. So normally it should not be necessary. But I experienced that there are some conflict between some temporary files. So unless you are doing something really perhaps easy, perhaps it's possible. But usually I create another calculator. Don't bother you with this. So here is some solution. So the calculator to get the file scan. So this was the previous script. And now with the loop. So here is how I did. So I use the enumerate function in Python, which is really handy. When you loop over a list, it can give you also the index of the list. So you save some lines. So I copy paste the previous script, and of course now this time the Z0 is changing each time in the loop. So I define the calculator, compute again. As before, I choose to change the title of my data to be more representative of what I'm doing. Otherwise the title is automatic, but that way you can change the title and give some useful information. And in the end, okay, not in the loop, because otherwise you will pop up each time a window, but in the end, you can view the data, okay? And if you do this, you will have this kind of results. So for 1.1 angstrom, you will have that figure. And now if I move my oxygen atom further, so 1.15, I start to see the intensity decreasing in place of the rhodium atom. Then it starts to be a quite dark area, okay, to 1.20 or 25. And then I move again my oxygen atom. And finally, I start recovering a maximum of intensity at 1.40, okay? So it means that, okay, and again, it means that according to that data, there are a move from 0.3 to 0.4 angstrom of the oxygen atoms is necessary between 2 intensity minima or 2 intensity maxima. Okay? And there are several images. You can see the interferences, clearly see the interferences, the change. So you can imagine that it is possible to achieve a resolution that is 10 times lower than this move. Okay, as they said in the paper. Is that okay for you? Was not too complicated? Yeah?
Is there a way to do this without plotting?
Without plotting? So you mean to find that value without plotting? Yes, sure, there is a way. There is only in Python there is always a way, but this is more programming effort. Yes, of course, you can view, you can analyze the data. So to access the data, so here is complex because it is a 2D data. So you have the value of the cross section for a couple of theta and phi. But in the data object, so here is the data object, okay? So there are plenty of data set in that data object. Each data set corresponds to a height of the oxygen atom. If you want to pick up a data set, for example, you choose the first one, for example. Okay, so this is a data set. And to access the values stored in the data set, you can use the name of the column which correspond to the variable. So for example, dataset.theta will give you the num-p array of all theta value. Dataset.phi will give you the num-p array of all phi value. And dataset.cross_section will give you all cross sections. So you can use this to analyze, to find. So you will have to look for a special point to find the cross section at a given theta and phi angle. You extract that value, and then you can make this. You can make this in your loop. Store the value in a other Python object of your choice, and print the result in the end. Of course, it's possible. All right. I share you this script. Okay, so I don't know at what time is the break, Didier? It's
half past in 15 minutes.
15 minutes. Okay, so we will start another tutorial which is really bigger and important because so for now this is just a simple calculation to show you some the process in photoelectron diffraction, so the forward focusing effect, the defocusing effect, the effect of the scattering factor. But now we will move to something more realistic. So we have to compute, typically you may have to compute the signal of a substrate, okay? So as you shine light on your substrate, of course you will excite atoms that are in the surface, in the subsurface, in a lot of planes of your sample, and in reality the total signal is the result of the sum of all diffraction patterns. So if you want to compute the total signal of a substrate, you will have to compute the signal from all the planes and to sum all these diffraction patterns to create the final PED pattern, okay? So I will illustrate this with a complex case, actually, which is aluminum nitride. Okay. So ALN, so it is an hexagonal structure, and this material can the tetrahedron inside the material can be oriented upward or downward. This is called the polarity, okay, of the ALN. So in a published paper in 1999, so a group they experimentally managed to grow both polarities of aluminum nitride, okay. So with a nucleation temperature, a lower nucleation temperature they promote the nitrogen side. So in this case, so the surface is nitrogen terminated, and the tetrahedron are pointing downward. And in the other polarity, if they grow, the nucleation temperature of the growth is higher, but the growth temperature is the same after, they were able to promote the aluminum side with tetrahedra pointing upward, okay? And they wanted to be sure about the polarity of such a sample. So what they did is to look at the photoelectron diffraction pattern, because if you look at the structure, the interesting thing is that the geometrical environment for the aluminum atom and the nitrogen atom for both polarities is actually the same, but just by exchanging nitrogen to aluminum. So the shape of the photoelectron diffraction pattern should change only due to the difference between the scattering amplitude. So it means that if you look at the diffraction, the PED pattern, you will see clearly the difference between both polarities. And they did that, and this is what they observed. For the aluminum side, in a full curve, and in the dotted curve is for the nitrogen side. And they clearly identified two peaks at around 30 degree and around 60 degree that will tell that this side, this polarity, this is the aluminum side. So we will try to reproduce that kind of curve. But when you think of it, it's really a lot of calculation, actually, because you have to compute the IL2P diffraction pattern. You have to divide it by the nitrogen 1s diffraction pattern, so you have to compute both. And you have to compute this for both polarities of the aluminum nitride, okay? And for a different plane of the aluminum nitride, because you are looking at the substrate, so there is contribution for the surface, subsurface, etc., etc., etc. And the bad news is that in the hexagonal cell of the aluminum nitride, they are inequivalent atoms. So it means that if you look at the cell of the nitrogen or ILN nitrogen side or aluminum side, you will have here nitrogen, two nitrogen atoms that are inequivalent, actually, because the tetrahedron is in a, so this is in that way here, but this is in that way here. So they are inequivalent atoms. So you have to compute this for two sides, aluminum and nitrogen, two emitter kinds each time. It means for nitrogen and aluminum, and two variants each time. And you will do this for a substrate, so you will look at the surface, the subsurface, and the sub-subsurface, okay? So 3 planes. So it means that you will have to build 24 clusters, okay? This is a more realistic example of doing a calculation. So 24 clusters to build. You compute the polar scan for those 24 clusters, and then you will have to analyze the results. So it means that you will have to sort which polar scan has to be divided with by which polar scan, okay? So it starts to be fairly complex. So basically, to treat this kind of problem, here is a kind of skeleton that you may use. So you will have, definitely, I think this is perhaps the best way to do, is to separate the creation of clusters in a separate function. Okay, so you will have a function to create your cluster. It will build up a list of all clusters that you have to compute. It will return the clusters, okay? So this is the first problem, okay? Create your clusters. Then you have to compute. So for all clusters, in each cluster in the list, you will have to make the calculation. So you can define a function to compute, okay, and to append the data. And finally, you will analyze the data. So here, you can divide your signal, make an average, make a sum, etc. And basically here, you will have to sum all the N1S signal for a polarity, a given polarity. You will have to sum all IL2P signal for a given polarity, and you will have to divide those two signals for a given polarity. Okay? So the good news for you is that it is almost written, actually. But there are holes in the script. So normally you have a script that is called ALN to fill or something like this. Yes. So this should be these things. Is that okay? You have this file? Okay. So if you look at this file, so there is the create cluster function. All functions are there, but there are holes. And the analysis function is almost, I guess it is totally written. So you don't care about the analysis function for the moment. When we will show the result, I will give some comments about this function. But you will just have for the moment to manage the creation of the clusters and the compute function. Okay? So just a few words about this function. So in Python, it is possible to use nested function. I don't know if you use them. So it means that it is authorized to create a new function inside a function. You can create a function inside a function. And this is useful. For example, here, I defined a get ALN tags planes function inside my create cluster function. Okay? So actually, the function starts here. The list of clusters is empty. And then I have 4 nested loops, of course, over the side, over the emitter, and over the plane to constrict my hemispherical cluster. And here, that part is to show you how to attach some information to the cluster. Because it is when you create a cluster, you lose the way you created it. For example, if you create a FCC 111 radium surface, you will have a list of atoms. Okay, but if you look at your cluster, you are not able to tell how you created it. So it may be interesting for you to, for example, add some information. So you can bundle some information using that keyword in the cluster object. So it's up to you now. Try to fill in the gaps in the first function. So the first line is actually to create the ALN cell, so primitive cell of ALN. So this is a Fürst crystal, and I gave you the A and C parameters. And the second line is important because you have to tag each. So by default, as I told you in the first tutorials, or in the second one, no, first tutorial. So the all atoms are tag 0. But if you want to identify them later, you need to tag them to be able to select them. So here, for ALN, you will tag the first 0, the second one, etc. Looking at the ALN sketch may help you to find which planes are to be used. So here, yeah, we want a list of plane numbers. So this is a little bit tricky, yeah. But it may help you to construct future script. Okay, so let's have a look at the first line. So easy. Bulk, ALN. So it means that it is known to ASE. Of course, sometimes you may have structures that are not known to ASE. And then you have to tag. So here is, for example, a way to tag. So it avoids a multi-line for loops, but you can do it with a multi-line for loop if you want, if you're more used to it. So it's a very compact writing in Python. And then so if the side is AL, aluminum, so you have to rotate the cell to move your tetrahedron upward. So here is how you can do it with ASE. So in the previous use of the rotate function, you remember we used an angle in the first argument and an axis name in the second argument. But ASE also understands this kind of notation. It means that my z-axis will be mapped to the minus z-axis. So it will understand this kind of rotation also. Okay. So if we are in the aluminum side, so the plane with the aluminum atoms are the even numbers. So my AL planes will be 0, 2, 4, 6, etc. Okay, but I am interested in doing only here 6 planes. So I will have 0, 2, 4. So for making a list in Python that will pick up only even index, you just have to put the step parameter here to 2. Yeah.
Doesn't this generate a generator? And so don't you need to do list after that?
It may, but it is only useful when you actually need a list. So it will stay, of course, a generator. So it is not mapped as a list, but I use it only in a for loop later. So it's no problem. So the nitrogen, of course, are the odd numbers, and of course for the other side, it is the opposite. And if the emitter is aluminum, what are the tags to be computed? So 0 or 2, because you tag your atom, so it is AlN, AlN. So 0 is aluminum, and 2 is aluminum, but 1 and 3 are nitrogen atoms. So you can check this by printing, for example, the first ALN object after you tag it. And that's it. So here is the main body of the create cluster function. So here is the trick. So for side in the aluminum or nitrogen side, so for emitter being aluminum or nitrogen, and here I use the function. So I will get the cell, the basic cell, the tags, and the planes that are used. And for emitter tag in tags, for emitter plane in planes, it's really tricky. Now you can create your cluster. So you have everything to create a cluster, one of the 24 clusters that you have to build. So you will use the hemispherical function. You have the emitter tag you have the emitter plane, you have the number of plane, so here it is. Okay, as usual, hemispherical cluster, the ALN basic cell. So the emitter tag is, of course, this variable, emitter tag. Emitter plane is emitter plane. And planes, so it is the total number of planes of your hemispherical cluster. So we choose to work with a cluster that have 2 planes below the emitter plane. So the emitter plane plus 2. It is usually a good idea when you make some photoelectron diffraction to have at least 1 plane below the emitter. Because otherwise you will never see the backscattering components of the last plane that may exist. And then you have to set the absorber. So the good news is, where is located the absorber? Okay, it has 24 different positions, but where it is? Easy. You have to use the get atom index. Of course, it is as you used the hemispherical cluster function, it is always located at the origin. And finally, you append this cluster that you just created, to the list of all clusters that at the beginning is empty. And you return the list of all clusters. So in the end, with this function, you will create all the possibility, all the clusters that you have to compute. And it's important to bundle such information, because for the next step, you will use a compute function. And the first argument of the compute function is the list of clusters. So you will have to be able to get the kind of emitter it is, and the side, of course, if you want to treat some information after. So it is one way to bundle information to your cluster, with your cluster. Okay, we shall make a break, perhaps, and see the compute function just after. All right for you?